Hello students, welcome to lesson number 3 of the topic machines. Machines is a topic which is taught in Form 3 and it is topic number 10 of physics. Previously, in the lessons 1 and 2 of the topic, we looked at the terms which are associated with this topic. Namely, we looked at what a machine is, and the terms associated with machines such as mechanical advantage, effort, work output, work input, velocity ratio, and the efficiency of a machine. We went on further to classify machines as force multipliers or distance multipliers, depending on what job they do in doing work. We also looked at a type of machine which is called levers, which we classified as first order, second order, and the third order levers. We also looked at the mathematics involved or related to levers. Today, in lesson 3 of the topic machines, we are going to look at a type of machine which is called pulleys. Pulleys. All right. We'll look at a type of machine called pulleys, or pulley systems, as they are sometimes called. So, what is a pulley? What is a pulley? Let us define a pulley. We define a pulley in physics as a grooved wheel mounted on a block. So we have, this is a pulley, all right? It has a groove. It has a groove where the string is passing. Is called groove. It's like a ditch. All right? It's like a ditch. So the string passes through this ditch called groove. All right? So this wheel has a groove through which a string passes. So the wheel cannot stand on its own. It needs to be supported. Right? So to get it supported, the wheel is mounted on a block. This part is called block. So in other words, a pulley is a system made up of 2 components, if not 3. It has a block, a wheel which is grooved, and a string, or sometimes called a rope. Rope. Okay? That's a pulley or pulley system. It's a wheel mounted on a block. So which part is block? It's this one here. And then we have a wheel which is mounted on the block, and then we have a string passing through a groove. A groove is something like a ditch. A ditch, eh? Alright. So a string or rope passes around the pulley, as shown here, and it is held in place by a groove so that it does not slip away. You know, this one which looks like a rim, eh? A rim, there is a ditch here, a space through which the string passes. Eh? Alright, so we are saying the string or rope, this can be a string or rope, passes through or around the pulley, and it is held in place by a groove. This is called groove, where the string passes. It's a groove, eh? Alright, so this is a pulley. It's a machine. It consists of a block, and this is where the wheel, which is pulley, is mounted, eh? Because the wheel on its own cannot stand in place. Eh? Yeah. Alright, so that's a pulley definition. Eh? What is a pulley? It's a grooved wheel. Groove is where the string passes. Eh? So it's a grooved wheel mounted on a block. This is a block. So it has a string or rope which passes around the pulley, and the string or rope is held in place by a groove. So the use of the groove is to hold a string in place. Eh? You can see already there. What is the use of the groove? Is to hold the string in place. Eh? All right. Okay, I'm sure you can't go wrong there on the definition of a pulley. What is a pulley? What is a pulley? It's a groove. It's a grooved wheel, eh? Mounted on a block, and it has a string or rope which passes around the pulley, and it is held in place of or by the groove. So on the pulley, a force called effort, denoted by the letter E, is applied on one end of the rope. Remember that a pulley has a rope. So when such a force is applied on the rope, it produces tension, T, tension in the rope. Tension, in other words, is the force which builds up in the string when it is pulled. Think about a string and you are stretching it, you are trying to apply a force on it. It becomes tight. The string becomes tight. The tightness is due to a force called tension and is denoted by the letter T. So this is the force in the string, eh? Or in the rope when it is pulled. Eh? All right? Such that this tension applied is equal to the force. The tension, the force in the string or rope is equal to the applied force, which is called effort. So the effort applied on the string, on the rope, creates a tension. So the tension in the string is equal to the force applied by pulling on the string. So that using symbols, E, effort, is equal to tension. So the tension in the rope is constant or uniform and acts in both directions along the rope. So when an effort is applied on the rope so that it creates tension in the string, the size or the magnitude of the tension in the string is uniform throughout the rope. And on the pulley again, there is a load L, which is supported by the total tension in the sections of the rope attached to the pulley on which the load is fixed. Alright, so the load is held in place by the force applied. This force is what we call tension, which is produced by the applied force, which is called effort. Alright, so the load is used to support, the load is supported by the total force in the string in all the sections of the string or the rope which is attached to the pulley on which the load is fixed. So what we are saying here is that we have a pulley here with a single wheel, and here we have a load. Load is mostly the weight which has to be lifted up when a force called effort is applied. So we are saying that by pulling this direction, pulling on the string, this string becomes tight. That tightness is due to a force called tension. Tension is force in a string when it is pulled. Alright? So the magnitude of the force, the tension, is constant. That's what they say, is constant. So the tension here is equal to the tension here, and that tension is the one that supports the load. Alright? So please take note of that. So F is force applied, and we're saying is equal to the weight, and rather the force in the string, which is constant everywhere, and it's the force which supports the load. Right. We have basically three types of pulleys. Basically, there could be others, but the main ones are three of them. Alright, so these pulleys are called fixed pulley. Alright, fixed pulley, it's type of pulley, that one. We also have a pulley which is called movable pulley. Movable pulley. And the third type is called block and tackle pulley. Block and tackle pulley. So three types of pulleys: fixed, movable, block and tackle. Three types of pulleys: fixed pulleys, movable pulleys, block and tackle pulley. Three types of pulleys. Alright, so let's look at what each one looks like. A fixed pulley is this one here, which consists of a wheel which is fixed, as the name suggests. So this wheel is fixed, meaning it's not movable. It does not go down or up. It's fixed, in fixed position. Alright, so a force applied here will lift the load up. That's how it works. Alright, in other words, it changes direction of the load. Okay, the load is acting down, its weight, due to its weight, but by pulling here, it will change direction, moving up. Alright, okay, so this load will go up due to a force called tension. That tension is created by the effort applied there. So it is named fixed pulley because this wheel does not move. All right, it's fixed. It does not descend nor ascend. The second type of pulley is what we call movable pulley. As the name suggests, it has a moving part. For example, when you pull this down, this lower pulley here will go up. As it is going up, it is also pulling along with it the load. All right, so pull here, it will cause this one to move up. The wheel, the pulley is going to move up so that the load is lifted up as well. So because it consists of movable parts, then this is called movable pulley. The third type is called block and tackle pulley. Block and tackle pulley consists of two parts. It consists of a part which is fixed, like here the upper part is fixed, and the lower part moves up and down depending on the direction of the effort. So when you apply the effort there, the upper part does not move. It's called block. This is called block, and the lower part moves, which is called tackle. So we have block and tackle. So the moving part will pull when an effort is applied there. This will pull the load and the lower part of the pulley system upwards, thereby doing work on the load. So please take note of the differences between these. We have fixed pulley here because it is fixed in place. It does not move up and down. Here we have a portion which is moving, which is capable of moving up when the effort is applied. So it's called movable pulley. This type of pulley, called block and tackle pulley, has the upper part fixed while the lower part moves. All right, take note of that. Take note of these types of pulley systems. So pulleys, how pulleys work is simple. Pulleys are used to change the direction of force and to gain mechanical advantage which is greater than one. All right, so we are saying that by applying a force here, an effort, the pail containing whatever, maybe water, is going to move up. Naturally, it is supposed to move down due to its weight, all right, because this is weight. So the direction of the weight is reversed by a force applied here. So we are saying the use of pulleys is basically to change the direction. In this case, the direction of the gravitational force, because we are looking at the load, which is the same as weight. So if we assume that the rope and the lower pulley are weightless, all right, where we have two pulleys or more assembled together in a system, all right, so assuming that the rope and the lower pulley are weightless and that the system is frictionless, there's no friction between the string and the wheel there, then tension in every part of the rope is the same. For example, here, the tension created in this part of the string due to the applied effort is the same everywhere, even here. That's very, very important. All right, but this assumes that there is no friction force between the string and the rest of the machine. The pulley to the right, this pulley here, the load L is equal to tension in the string, in the rope, all right? So for this load to be lifted up, the force applied must be equal to the load itself. Then this is going to be lifted up. All right, that's why when you are applying an effort here, make sure that the effort you apply is equal to or greater than the load, so that it is capable of moving up. If the effort applied is less than the load, then it will be impossible for this to move up. Rather, it will move down. So to counteract the gravitational force and all that, the resistance that comes with it, you need to apply an effort which is equal to or greater than the weight of the pair and what its contents there. All right, very important to note. So we are saying, in this case, we're saying load is equal to tension in the string, and is therefore equal to load equal to effort. All right. Why are we saying this? Is because tension, we said tension is equal to effort. The effort applied there is equal to the tension in the string. So in order to move this body, the pair, with what I need or whatever is inside, we need to apply a force equal to or greater than the weight. So let's suppose that the load is equal to the tension applied. Then we can conclude that effort is equal to load. How do we work out the mechanical advantage and velocity ratio of a block and tackle pulley? Remember that a block and tackle pulley consists of the upper part, which is fixed, and the lower part, which is movable. So the upper part is called block, the lower part, which is tackle part, is called tackle. So in this case, in the system on the right, we have a system here, all right, consisting of a tackle. This is the block, and a tackle down here, which is movable, right? So in the system on the right, mechanical advantage is calculated in the following manner. All right. The load on the system here is simply equal to, is supposed to be equal to the tension applied. All right. So that tension is the tension in all the parts of the string. So this string has 4 parts. If you look at it carefully, it has 4 parts. It has 1, 2, 3, 4 parts. All right. So this tension altogether must be equal to the load here. All right. You don't include this part here. We are only referring to the parts of the string that are below, below the system. All right. Supporting the load. All right. The parts of the string supporting the load, they are the ones we count. So we are saying the tension in all these 4 parts together should be equal to the load, all right? But we said that tension is equal to effort. The effort applied here is equal to the tension in all the parts of the string. Here, the tension here, the tension here, the tension there, is equal to the same force which is being exerted at this point. Please take good note of that. So where there is a T here, we can substitute, we can put an E, so that what we have now is 4E, because we are saying T is equal to E. So 4E, where E is effort, is equal to the load. All right. So in this case, if we bring in the definition of mechanical advantage, which we learned about last time, we said that mechanical advantage is load over effort. So if we divide this equation by effort, both sides, divide this side by effort, this side by effort, dividing load by effort gives us mechanical advantage. So dividing both sides by effort E will give us this equation here. So the effort is common here, all right? You can see the effort is common, so therefore mechanical advantage is simply equal to 4. All right, notice that this 4 is just the same as the number of sections of the string. 1, 2, 3, 4, or simply count the number of wheels. Coincidentally, the numbers are the same. The number of wheels and the number of parts of sections are also the same. So mechanical advantage is equal to 4. So, for a system which is assumed to be perfect, like no friction, no energy loss, it has been seen that mechanical advantage of such a machine is also equal to its velocity ratio. So when the mechanical advantage is equal to 4, it means the velocity ratio is also equal to 4. So if the load moves a distance of d, for example, the effort is supposed to move through a distance of 4 times, generally, all right? Where this 4 here depends on the number of sections of the string. So here we have 1, 2, 3, 4. So this 4 is coming from the number of sections. So we are saying if it moves a distance of d meters, then the effort moves through a distance of 4, thereby increasing the mechanical advantage of the machine. It needs to be noted that in a perfect Pulley system is one in which friction force is ignored, there's no energy losses. Okay, so such a Pulley is said to be a perfect one. It's like ideal, all right? So in a perfect Pulley system, the mechanical advantage MA is equal to the velocity ratio, all right? And both are equal to the number of sections of the string. So to find mechanical advantage of a Pulley system without calculation, all you have to do is count the number of strings that the system has. The number of sections of the string the system has will give you the mechanical advantage, which we say is equal to the velocity ratio. All right. Also note that the here is supposed to be the part of the block in the lower section of the system, and the friction in the pulley reduces the mechanical advantage. All right, the weight of the block. This is supposed to be the weight of the block in the lower section of the system, and the friction in the pulleys reduces the mechanical advantage of the machine. Remember, yesterday we pointed out that the reason why machines are not 100% efficient is because of energy losses. Energy losses due to friction between parts, but also machines. There are some machines that some parts of the machine that are not useful, and when the machine is being used, those useless parts lead to loss of energy, thereby reducing the energy output or the work output. So we are saying the weight of the block in the lower section of the strip system and the friction in the pulleys will reduce the mechanical advantage of the system. Hence, the mechanical advantage is usually less than the velocity ratio, all right, because of such energy losses. And also note that the velocity ratio of a Pulley system is numerically equal to the number of string sections. We have mentioned this before, all right, which are supporting the load, all right. So in order to find mechanical advantage without necessarily applying the formula load over effort, just look at how many sections of strings are supporting the load. Just count them. The number you get is going to be equal to velocity ratio without calculation. Without calculation. All right. So if you look at this Pulley system here, without calculation, you see it has 1, 2, 3, 4. All right, 4 parts. The system has 4 sections of strings. So that means its mechanical advantage is 4. Incidentally, the number of sections here is also equal to the number of wheels. So you count the number of wheels, we have 4. the number of sections of this tree, we also have 4. Therefore, the velocity ratio of this machine is 4, as well as its mechanical advantage is 4, without having to carry out any calculation. For example, in the figure below, we have 3 pulley systems. All right, we have this pulley here with 2 wheels, or 2 parts of sections of string, and over here we have 5 wheels, while here we have about 6. Of course, the diagram is not clear, but it will still save what we want. Alright, so in each case we are asked to calculate velocity ratio, a mechanical advantage, and the efficiency. Alright, so like we said, velocity ratio is simply equal to the number of parts of strings or sections. So here, for the first part, obviously you can see that this one has a velocity ratio of 2. Just count the number of sections there. To calculate mechanical advantage, simply apply the formula. Mechanical advantage is equal to load, which is given here, divided by effort, and you find the result there. For efficiency, again, you apply the formula which you know already. That formula says mechanical advantage or efficiency is equal to mechanical advantage divided by velocity ratio multiplied by 100%. Okay, so you apply those equations in all these, in each one of them. All right. So please master the calculations, because you have to demonstrate the same, that you understand them in an exam. All right. So once again, to find mechanical advantage, or rather velocity ratio, just count the number of sections. Here you have, of course it's not clear, it's not very clear, but you have 1, 2, 3, and 4. So velocity ratio is equal to 4. Here it has 6 parts. If you can't count the number of sections, just count the number of wheels. It is going to give you the same result. So mechanical advantage here is going to be, you use the values given, because sometimes, because of friction or something else, mechanical advantage can be less than the velocity ratio. All right. Okay, so see how this could be done. All right, so in the first case, we have this one. We have this pulley here. We have this pulley here, which has 2 sections supporting the load. It has this section here and this section. So mechanical advantage, or rather velocity ratio, is simply equal to 2. How? You just count 1, 2. Just count the strings. Don't do anything. Just count the strings, unless you have more information to help you to use any calculation. All right. Mechanical advantage, you need to apply a formula again, since both load and the effort are given. So all you do is apply the formula. Mechanical advantage is equal to load divided by effort. So in this case, our load is 210, while the effort is 150. So you divide 210 by 150, it will give you the result of 1.4. Remember that mechanical advantage is a unitless quantity, so there is no need to put a unit at the end there, because the units of force, which are the newtons, have cancelled out in the calculation here. We have Newton on top, Newton down here, so the two are going to cancel out to give us 1.4. Please use your calculator to verify that indeed this is the result obtained when you divide 210 by 150. Both of them are newtons, so that we have a value which is unitless. So once again, mechanical advantage is calculated from load divided by effort. But for a perfect system is one which does not cause energy losses due to friction. Such a system, the mechanical advantage is simply equal to the number of sections of the string. So it could be 2 as well. While efficiency, to find efficiency or to calculate efficiency, all you have to do is to apply the formula of efficiency. We say efficiency is equal to mechanical advantage divided by velocity ratio, not forgetting to multiply the result by 100%, because efficiency is expressed as a percentage of the work input. So substituting, we already got mechanical advantage up here. Always remember what you have got before, all right? Don't lose track. So the mechanical advantage here is 1.4, and we substitute this into the equation. We have 1.4 over 2 times 100%. So the result is going to give us 70%. So this machine is 70% efficient. Not good, because it means the other 30% is lost energy. All right, it's lost energy. So 70% is okay, but not quite good. Not quite good. All right, so go through this a number of times until you master the step-by-step approach of solving this. Open an eye to what is given, and keep your eye open to what is given in the question. All right. For the second part, velocity ratio is equal to 5. Why 5? You simply count the number of sections of the string. So here you have 1, 2, 3, 4, and 5. You don't count this one here. This one is not part of the, it is not supporting the weight down there, no. But these 5 are the ones that we are interested in. So velocity ratio is going to be 5, or simply count the number of wheels. While mechanical advantage is calculated from the formula once again, mechanical advantage is load divided by effort. So in this case, our load is 210 and the effort is 60 newtons. Both of them are newtons. So you divide the load by effort, it will give you 3.5 without units. Again, efficiency is going to be mechanical advantage calculated up here divided by velocity ratio already calculated there, multiplied by 100%. So when you calculate this, you should be able to get something like this. 3.5 comes here, the denominator, the numerator rather, and 5 on the numerator here, denominator, and multiplied by 100. So that will give you the efficiency of the machine. It is again equal to 70%. Again, not a good sign, it's not a good machine, because it means that 30% of the energy is wasted through lifting of the useless parts of the pulley system and the frictional force between the string and the pulleys. All right, once again, make sure that you are able to follow on this, and if you have questions, don't hesitate to ask so that we can clarify things together. So I think I'll share with you the diagram later. All right, I'll share with you the diagram later, which you can use to answer this question. When you finish learning, just remind me to send you the diagram in question so that you can use it to answer this question here. So we are told that in the Pulley system shown, an effort of 120 newtons is required to lift a load of 200 newtons. Calculate the distance through which the effort moves when the load is lifted through 1.2 meters. So the work done by the effort, alright, the work done by the effort, calculate that. It all depends on the figure that I'm yet to give you when you are through with your learning. Just tell me to send you the diagram. I have the diagram. I'll send it to you so that you can work on this question. Otherwise, I wish you all the best. This marks the end of our lesson today. It has been a 40-minute lesson, close to a period, a normal period. All right, so thank you very much. I wish you all the best. We meet again in the next lesson. Once again, bye-bye for now.